Welcome to the Human-Robot AI Interaction Seminar. Today's presentation will focus on intuitive human-robot interactions. Let's start this presentation with an easy question. How many of you like sci-fi movies? Raise your hands if you do, and think about some examples. Here we have some examples of broadly famous sci-fi movies. Think, what do you think sci-fi movies have in common? The answer is human-AI interaction. In many sci-fi movies, there are represented interactions between humans and artificial intelligence, AI. These AIs can be embodied such as in robots, or they can be integrated into software without embodiment, like in social media. Along this presentation, we are going to explain and show how different ways of creating intuitive human-robot interactions by showing examples of science fiction and real cases of the same type of interaction. During the presentation, we are going to follow this outline. First, we had a small introduction about the topic and understanding what human-AI interactions are. Next, we will present 5 different ways of making interactions between humans and robots more intuitive, and we will dive into each one of them giving examples based on sci-fi and real cases. Finally, we will conclude the presentation with some important bullet points about the topic. What are intuitive human-robot interactions? Intuitive human-robot interactions are methods of interacting with robots which are easy to perform for human beings. The majority of these interactions use non-verbal information which is captured with sensors and translated into commands or policies for the robots. In this presentation, we will focus on robot commanding, teleoperation, extended reality interactions, and emotional cognitive adaptation. Let's begin with robot commanding. Robot commanding involves the precise control and direction of a robot's actions and behaviors. This is achieved through a spectrum of methods and commands, essentially serving as the set of instructions that guide a robot's movements and tasks. How can we make commanding robots feel as natural as possible? We achieve this through 2 main channels, non-verbal and verbal communication. Regarding non-verbal communication, imagine controlling a robot with just a wave or a point. Non-verbal cues, like hand gestures, allow us to convey commands to robots intuitively. It's like having a conversation without saying a word. Voice commands are another powerful tool. We speak, and the robot listens. It's like having a virtual assistant that doesn't just answer questions, but acts on our commands. The first example is from a Star Wars series, in which we can see the main character, the Mandalorian, use a mix of gestural and voice commands to guide the robot on how it can help him to fulfill the tasks.
Can you stop moving? Just focus right here. Yes, thank you.
Trust me, the last thing you want strangling your thrust capacitor is a vapor manifold. I fabricated you this induction intake charger that's going to double your output coefficient.
Where does this panel go? Thanks, little guy.
In the second example, we can see Tony Stark from Iron Man welding and assembling part of his armor, and mainly using voice commands to communicate with his assistant robot.
Next. Up. Not complete, dummy. Right here. Got me. Stay put. Nice. You're no benefit at all. Move down to the top. I got it. Okay, I'm sorry. Am I in your way? Up. Screw it, don't even look. You are a tragedy.
How can we bring the concept of gestural interaction to life through practical implementation? First, it is necessary to use devices to capture hand gestures, for example, using data gloves. Data gloves capture your hand gestures, translating the subtleties of movement into data that the robot can interpret. It's like giving your robot a set of eyes to understand your physical cues. Now that we have the gesture data, the next step is making sense of it. We need to translate this raw information into commands or policies that the robot understands. Think of it as turning your hand movements into a robot-friendly language. One crucial aspect is understanding the context of the interaction. Robots need to know not just what we're doing, but also why we're doing it. Context-aware commanding ensures that the robot responds appropriately to the situation. Now let's dive into a real-world use case of gestural interaction. The Component Multimodal Online and Offline Programming Solution, M2O2P, was developed in the European project shop 4CF. This component allows the user to interact with a computer and a collaborative robot, cobot, by using hand gestures. The worker wears data gloves that capture the gestures performed. In the videos, you can see how the human worker can start and stop the execution of a task, opening and closing the gripper, and record new trajectories. The gestures are selected to be as intuitive and different as possible, which also increases the robustness of the algorithms. Now let's turn our attention to verbal interaction and see how we can make it a practical reality in human-robot interactions. Firstly, when it comes to verbal commands, capturing the user's request accurately is crucial. Using specialized devices to capture audio data, ensuring that every word you say is recorded and ready for processing. Once we have the audio data, the next step is converting it into text. This is where speech-to-text models come into play, transcribing the user's spoken requests into textual format. With the text in hand, we can input the user's text request into an AI-based task planner which deciphers the textual requests and translates them into actionable steps for the robot. Finally, the robot runs the functions corresponding to each of the steps, provided completing the user's request. In addition, context matters. Understanding the context of the interaction is crucial for accurate and meaningful responses. Whether it's the environment, the user's intent, or the specific situation, considering context enhances the quality of human-robot interactions. Let's see a real use case on how we can command robots using language. The Google Robotic Transformer 2, RT2, represents a cutting-edge fusion of vision-language action capabilities, harnessing web and robotics data knowledge to craft generalized instructions for robotic control. RT2 transcends linguistic barriers, enabling users to command robots in diverse languages, thereby fostering global accessibility and inclusivity in human-robot interactions. Let's see the video.
This is the research team at Google and their partners at Everyday Robots. They work on cutting-edge research in machine learning, natural language understanding, and robotics. They train language models to understand questions, reason out answers, even understand when something is funny. Funny in the loosest sense of the word. Language models power much of the helpful technology we use online today. But imagine if they could not only understand you, but work with something in the real world that could learn to help you out. Working together, these researchers have combined the latest language model with the advanced capabilities of a helper robot. Each task is broken down into simple behaviors. Then, these steps are given a likelihood of succeeding in the physical world. Sounds easy. But this is seriously difficult stuff. Because for learning robots, sometimes the smallest things can be the hardest to grasp. But research like this brings us one step closer to robotics that make our everyday lives easier. One step closer. Good job.
Now let's switch the focus to teleoperation. Teleoperation is about controlling a system, be it a machine, device, or robot, from a distance. This technology is based on remote control technology to bridge the distance between the operator and the system. Through communication technology such as high-speed internet, radio waves, or satellite links, we can send commands in real time. Apart from sending commands, it is necessary to receive feedback which can be received as visual cues, haptic feedback, or even telemetry data. Finally, for teleoperation to work properly, it is crucial to have minimal latency. This ensures that operators can interact with systems as if they were right there on site. The first sci-fi example is from Black Panther. We can see that Shuri, located in Wakanda, is teleoperating a car located in South Korea, performing a chase.
Let's go! Go, 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 come on!
Do we just leave him? He'll catch up.
Shuri!
Remote driving system activated.
Wait, which side of the road is it?
For boss sake, just drive.
Okay, calm down. Woo! Let's go!
Put some music on. What do you think this is, the funeral?
Which one is he in now?
Hey, split up!
They're trying to lose us. We'll take the right. We'll take the other two. I see a shortcut.
Then, in the second example from Real Steel, we can see how the child is teleoperating a robot which mimics his movements. In the following use case, we can see how a person is teleoperating two robotic hands to play Jenga. This is to demonstrate the precision of the operating system. The operator is wearing a pair of data gloves which have trackers in the tip of each finger. Together with a tracker on the forearm, the system senses the position of the whole hand and translates the movements to the robotic hands. Depending on the application in which teleoperation is needed, some use cases might integrate force and haptic feedback in their systems. Teleoperation is applied to different scenarios, such as remote surgery, handling hazardous materials, for example, toxic materials or explosives, or operating in harsh environments, for example, deep-sea exploration or space missions. Extended reality, or XR, serves as a comprehensive umbrella term that encapsulates a range of immersive technologies. Virtual reality, VR, a fully immersive experience that transports users to a completely virtual environment. Augmented reality, AR, overlays digital content onto the real world, enhancing our perception and interaction with our surroundings. Mixed reality, MR, blends elements of both VR and AR, allowing digital and physical objects to coexist and interact in real time. To take advantage of the potential of XR, we need sophisticated interfaces that facilitate interaction with digital elements. This involves gesture control, using hand movements or body gestures to navigate and interact within XR environments. Voice recognition and haptic feedback. At its core, XR aims to transport users into immersive realms that engage multiple senses, such as visual, auditory, haptic, or olfactory. Regarding the sci-fi examples, on one hand, we have Ready Player One, where is introduced a virtual world named the Oasis, where users can engage in any kind of experience by connecting to their XR devices.
James Halliday saw the future, and then he built it. He gave us a place to go, a place called the Oasis. This is the Oasis. It's a place where the limits of reality are your own imagination. You can do anything. Go anywhere. Like the Vacation Planet. Surf a 50-foot monster wave in Hawaii. You can ski down the pyramids. You can climb Mount Everest with Batman. Check out this place. It's a casino the size of a planet. You can lose your money there. You can get married. You can get divorced. You can go in there. People come to the Oasis for all the things they can do, but they stay because of all the things they can be. Tall, beautiful, scary, a different sex, a different species, live action, cartoon. It's all your call. Yeah, that's me. Well, that's my avatar. At least until I feel like changing. Except for eating, sleeping, and bathroom breaks, whatever people want to do, they do it in the Oasis. And since everyone is here, this is where we meet each other. It's where we make friends. Locate H.
Locating H.
On the other hand, there is Free Guy. In this example, the main character discovers a set of glasses which shows him a mixed reality. While using the glasses, he can see and interact with digital elements that before he was not able to see.
Excuse me. Do you see this?
A quarterly reports on my desk by Friday.
Feel brand new.
Money on my mind, so to pay. Real hard of time, never Kool-Aid, sipping on Goose sight. Came a long way from Pittsburgh, putting in work like Ferg. New York to LA.
What is happening?
We have explored the essence of XR technologies. Now let's go further into how we can bring these immersive experiences to life. At the heart of XR interactions lies the creation of digital elements that populate virtual, augmented, or mixed realities. This involves 3D modeling, crafting three-dimensional objects and environments that users can interact with. Animation, bringing these digital elements to life through movement and behavior, and integration, seamlessly blending digital elements with real-world environments, whether it's overlaying augmented content or embedding virtual objects within physical spaces. To experience XR, users rely on specialized hardware and wearable devices including XR headsets, audio input-output, and controllers. Also, spatial computing is the backbone of XR, enabling the seamless integration of digital and physical worlds. This involves mapping, accurately representing physical spaces within XR environments, allowing for precise interactions and spatial awareness, and overlay, placing digital elements within real-world contexts, whether it's annotating physical objects with augmented information or integrating virtual content into our surroundings. Finally, in XR interactions, avatars serve as our digital counterparts, representing us within virtual or mixed realities. Avatars allow us to reflect our appearance, movements, and even expressions, capturing the essence of our presence, and enable social interactions within XR environments, allowing us to communicate, collaborate, or compete in a digital space. In the slide, you can see some examples of XR implementations such as Pokémon Go, Apple Vision Pro, and Meta's Pixel Codec avatars. Now let's see some real-world applications in the field of human-robot collaboration. Here, we present two applications, both focused on training operators on an assembly line. In the first one, the user is following the steps to assemble a camera, having the assistance of a cobot, whereas in the second one, the user is training their skills on a collaborative task with a cobot assembling a wooden box. One of the standout applications of VR is its capacity to train individuals in a risk-free simulated environment. VR platforms can simulate robot programming interfaces, allowing users to practice coding and command sequences without the risk of real-world errors. Also, trainees can operate virtual robots, honing their skills in tasks like navigation, manipulation, and task execution, all within a controlled virtual setting. Additionally, VR enables users to practice collaborating with virtual robots, fostering teamwork and understanding of human-robot dynamics without actual physical presence. Before investing in physical robots, organizations can leverage VR to simulate various collaboration scenarios, assessing how humans and robots interact, communicate, and perform tasks together in different contexts. Identify potential challenges or safety concerns in human-robot interactions and devise strategies to mitigate risks. And refine human-robot collaboration protocols based on insights gained from VR simulations, ensuring smoother integration and operation in real-world settings. Finally, VR elevates human-robot collaboration by offering accurate tracking and motion sensing, and intuitive control interfaces. Let's dive into the emotional cognitive adaptation. Emotional cognitive adaptation refers to the AI's ability to dynamically adjust its parameters or behavior to better align with the needs and preferences of the human it interacts with. Essentially, it's about AI tuning in to human emotions and cognitive states to foster more meaningful and beneficial interactions. An AI system can perform the most beneficial adaptations by sensing human reactions, analyzing the acquired data, translating the data into states, and performing the adaptations. As sci-fi examples of emotional cognitive adaptations, in the first case, we have a scene of Iron Man 3. Here, Tony Stark doesn't feel good and runs to his armor, in which his AI assistant runs an analysis, checking his vital signals and giving a diagnosis.
Sorry. It's Jerry. heart. Check the. Is it the brain?
No sign of cardiac anomaly or unusual brain activity.
Okay, so it's poison.
My diagnosis is that you've experienced a severe anxiety attack.
Me?
Come on, man. This isn't a good look. Open up.
Sorry, I gotta split.
The second example is from the movie Chappie. Here, the robot, Chappie, is interacting with two humans. It reads their emotional and cognitive states and mimics and adapts to them, mainly using body language and voice tone that makes the humans feel comfortable.
Chappie, look. Rats.
Nah, he's stupid. He don't know how to talk. We're screwed.
No, he can talk. He's smart.
No, he can't talk. He's smart.
What?
Oh my God! Look, he's copying me.
Chappie, say Hugh.
Shoe.
Say rat.
Rat.
Say mommy.
Say mommy. Chappie.
Hugh.
Rat. Mommy.
America.
America Holmes.
America Holmes.
This is good, Chappie.
Oh, shit. That Holmes is a clever little robot right there.
That Holmes is a clever little robot right there.
Oh, hey, this motherfucker talks ghetto, huh?
This fuck mother talks ghetto, huh?
All right, you the rudest bad boy in Joburg.
Chappie be the rudest bad boy, streetwise professor in Joburg, fuck mother.
Yes, it's gonna work, man. Oh, I can work with this. Yes, this is good. All right, let's pound it out. Like this. Go. Bloop.
Boom, Chappie. Boom. Boom. Go.
In the next slides, we will dive deeper into these steps. To truly understand emotional cognitive adaptation in AI, it's essential to explore the psychophysiological background from which these states originate. Let's dive in. The nervous system serves as the body's intricate command center, orchestrating a myriad of functions and responses. It's a complex network comprising neurons, specialized cells transmitting nerve impulses, facilitating communication within the system, tissues and organs, structures like the brain, spinal cord, and peripheral nerves that work in harmony to control movements, automatic responses to stimuli, digestion, breathing, sexual development, and more. Situated within the broader nervous system, the autonomic nervous system plays a pivotal role in regulating involuntary body functions. It oversees a range of activities including brain functions, influencing cognitive processes and emotional responses, cardiovascular system, regulating heart rate and blood pressure, muscular system, modulating muscle contractions and movements, respiratory system, managing breathing patterns, and eye activities, controlling pupil dilation and other ocular functions. Complementing the nervous system, the endocrine system serves as the body's regulatory network. It employs hormones, chemical messengers, to coordinate a multitude of functions. Metabolism, growth, emotions, sleep. Understanding this psychophysiological landscape offers valuable insights into the origins of emotional and cognitive states. It is crucial to understand the foundational concepts of emotions and cognitive states. Emotions are intricate reaction patterns that encompass both psychological and physiological elements. They emerge in response to various stimuli, be it internal thoughts, external events, or environmental factors. Some common emotions include disgust, anger, joy, sadness, and fear. Cognitive states pertain to an individual's mental conditions, shaping their ability to acquire, process, store, and utilize information. These states significantly influence cognitive functions and performance. An example of a cognitive state is the flow state, also known as being in the zone. Characterized by deep immersion and focus, the flow state represents optimal performance and engagement. It's a state where individuals feel fully absorbed in the task at hand, often losing track of time and experiencing heightened productivity and creativity. As we are using movies as examples, Disney Pixar's movie Inside Out shows and explains 5 basic emotions, and Disney Pixar's movie Soul shows the cognitive state of flow. In the context of Industry 5.0, which emphasizes human-machine collaboration and the integration of advanced technologies in industrial settings, some of the most relevant emotions and cognitive states are physical fatigue, attention, cognitive workload, and stress. Understanding and addressing these states are pivotal for promoting a harmonious, productive, and safe Industry 5.0 ecosystem. As mentioned in the introduction slide of the emotional cognitive adaptation, we can implement this in an AI by sensing. This implies capturing psychophysiological signals using the proper techniques and wearable devices for the scenario of the interaction. Performing an analysis of the signal parameters to extract meaningful insights and integrating data from multiple sources, enhancing the richness and accuracy of the analysis. Translating raw data into actionable states, employing algorithms or machine learning models to categorize signals into specific emotional or cognitive states. Additionally, it should incorporate contextual information. Lastly, it should be implemented the appropriate adaptations based on the identified states. To achieve it, it should be programmed adaptive responses ranging from adjusting system parameters to altering user interfaces, among others. When it comes to capturing signals for emotional cognitive adaptation, 2 primary categories emerge: psychophysiological signals. These signals predominantly represent unconscious processes within the body. Given their involuntary nature, these signals are inherently challenging to deceive or manipulate, offering a more genuine representation of internal states. And physical signals. These signals encompass physiological activities that can be consciously controlled to some extent. While they provide valuable data, there's a potential risk of imitation or deliberate manipulation, making them somewhat more susceptible to deception. Within the human body, various regions and activities serve as rich sources of psychophysiological and physical signals. These activities are brain activity, cardiovascular activity, electrodermal activity, muscular activity, respiratory activity, and ocular activity. In the context of emotional cognitive adaptation, sensing brain activity implies monitoring electrical patterns and neural oscillations to obtain information on cognitive states and emotion levels. For this, electroencephalography, EEG, serves as a non-invasive and powerful tool for capturing neurophysiological functions. EEG is a non-invasive technique that captures and records the electrical activity generated by the brain's neurons. Electrodes are strategically positioned on the scalp, forming an array that captures electrical signals emanating from underlying brain regions. As neurons within the brain communicate and synchronize their activity, they generate electrical impulses. EEG captures these synchronized neural firings, reflecting various cognitive and emotional states. The captured electrical signals undergo amplification to enhance their visibility and clarity. Later, the amplified signals are then displayed on screens, computer interfaces, or even printed on paper, allowing for real-time monitoring and analysis. The brain's activity is dynamic, reflecting the ever-changing states and experiences of the individual. Depending on various factors such as arousal level, task engagement, or emotional state, the brain exhibits distinct patterns of electrical activity. Different frequency bands correspond to specific states and activities, offering valuable insights into cognitive and emotional dynamics. There are different types of brain waves such as delta, theta, alpha, beta, and gamma waves. Cardiovascular activity focuses on capturing metrics like heart rate variability, and blood pressure. The electrocardiogram, ECG, emerges as a pivotal technique in capturing the rhythmic activity of the heart. ECG is a non-invasive technique that captures and records the electrical activity and rhythm of the heart. ECG provides invaluable insights into cardiac health, rhythm irregularities, and autonomic nervous system activity. In ECG, electrodes are strategically positioned on the precordium, chest area over the heart, and limbs, creating a comprehensive mapping of the heart's electrical field. As the heart undergoes its rhythmic contractions and relaxations, it generates electromagnetic currents. ECG captures and interprets these currents, reflecting the heart's activity and function. Then, the captured electrical signals are amplified to enhance their visibility and clarity. Lastly, amplified signals are then displayed on screens, computer interfaces, or printed on paper, enabling real-time monitoring, analysis, and interpretation. Electrodermal activity, EDA, often referred to as galvanic skin response, GSR, is the biofeedback signal arising from minuscule fluctuations in the skin's electrical conductance. EDA serves as a sensitive indicator of sympathetic nervous system, SNS, activation. EDA signals are comprised of two main parts: skin conductance response, SCR, which reflects the short-term changes produced in the humidity of the skin, and skin conductance level, SCL, which represents the long-term average level of conductivity created by sweat during a specific time frame. Muscular activity is governed by the interplay of motor neurons and muscle fibers. Electromyography, EMG, captures and records the electrical signals generated by motor neurons, reflecting muscle contraction and activity. EMG serves as a powerful tool for assessing muscle function, movement patterns, and neuromuscular dynamics, offering insights into physical performance, biomechanics, and motor control. EMG can be performed as invasive or non-invasive. Invasive EMG involves inserting a needle electrode directly into the target muscle, allowing for precise recording of intramuscular electrical activity. It is predominantly utilized in medical settings for diagnostic purposes. Non-invasive EMG involves placing surface electrodes on the skin, overlying the muscles of interest, capturing the electrical activity during muscle contractions. It has been widely adopted in engineering and research settings for evaluating muscle function, analyzing movement patterns, and exploring possible interactions with devices. Respiratory activity focuses mainly on monitoring breathing patterns and respiratory rates. Respiratory motion monitoring, RMM, are techniques which employ strain gauges, textile-based /resistive strain sensors, wire strains, or foam-based pressure sensors to record and analyze chest wall movements. RMM provides non-invasive ways to assess respiratory dynamics, offering insights into breathing patterns, thoracic movements, and respiratory efficiency. Unlike invasive techniques that measure parameters like oxygen uptake, VO2, and carbon dioxide output, VCO2, RMM focuses on capturing the mechanical aspects of respiration without directly analyzing gas exchange. Ocular activity in emotional cognitive adaptation refers to tracking eye movements, pupil dilation, or blink rates. Eye tracking methodologies, such as infrared oculography, IOG, capture and analyze ocular movements, providing insights into visual attention and gaze patterns. There are two types of eye trackers: remote eye trackers, which consist of a camera and infrared source capturing eye movements within a designated headbox boundary. They are widely employed in screen-based scenarios. And mobile eye trackers are designed as wearable devices, often taking the form of glasses or headbands equipped with cameras targeting both the eyes and the user's field of view. They are ideal for real-world scenarios and dynamic contexts, offering insights into everyday visual experiences, interaction dynamics, and embodied cognition. Continuing with sci-fi versus real-world examples. In the top video, we can see an example of the movie Iron Man, where Tony Stark is testing his armor, and it appears a circle tracking where he is looking and giving information about it. On the other hand, the bottom video shows a real scenario in which a human worker is assembling a wooden box, and there are indications of his gaze movements with circles.
Jarvis, you there?
At your service, sir.
Gauge heads-up display.
Check.
Four-door preferences from home interface.
Will do, sir.
All right, what do you say?
I have indeed been uploaded, sir. We're online and ready.
We start the virtual walk-around?
Importing preferences and calibrating virtual environment.
Do a check on control surfaces.
As you wish. Test complete. Preparing to power down and begin diagnostics.
Yeah. Tell you what, do a weather and ATC check. Start listening in on ground control.
Sir, there are still terabytes of calculations needed before an actual flight is achieved.
Jarvis, sometimes you gotta run before you can walk. Ready? In 3, 2, 1. Kind of like a dream.
The next two slides show tables in which it is shown some of the main parameters to take into consideration while analyzing data coming from the physiological activities that we have seen before. These tables target a specific emotional or cognitive state, having a table for each of the main states for Industry 5.0. Physical fatigue, attention, cognitive workload, stress, and trust are covered in these tables. In the emotional cognitive adaptation, a pivotal challenge lies in translating rich physiological data into meaningful emotional and cognitive states. A common way to represent emotions is by using the pleasure-arousal dominance PAED model. The PAED model presents a three-dimensional space composed by pleasure, or valence, which reflects the emotional tone of an experience, categorizing emotions as positive or negative. Arousal, that represents the intensity or activation level of emotions. And dominance, that differentiates emotions with similar pleasure-arousal values by assessing the perceived control or influence over a situation. Additionally, some emotions and cognitive states can also be extracted from the analysis phase, as some signals are strongly related to certain states. Lastly, we must perform the adaptation to the emotional and cognitive states that we have detected. For it to happen, firstly, we should define the context in which the adaptation takes part. This means establishing the interaction dynamics that influence the adaptation, environmental factors, and situational parameters that might influence the interaction. Some contextual variables could be the user's locations, task demands, workstation settings, time constraints, or production constraints. Secondly, we should generate a user profile for the activity that is going to be performed. The profiles should include information that can influence the activity to be performed, such as their emotional and cognitive states, biometrics data, or demographic information. To acquire quality data related to their internal states, it is necessary to perform tests measuring the user's response. Finally, taking into consideration the information coming from the context and the user's profile, we should program how the AI is going to change its behavior. This includes developing adaptive logic, using algorithms, decision-making frameworks, or rule-based systems. By integrating real-time monitoring and establishing decision thresholds, we facilitate contextually appropriate adaptations. Now, a real use case for this adaptation was developed as for an emotion-driven human-cobot interaction. To achieve the goal of making a cobot adapt to a human worker's internal state, we followed the steps mentioned in the previous slide. Firstly, we defined the context of the adaptation. Our use case is part of Industry 5.0, which takes into consideration the integration of human-centric technologies, cobots, and adaptive systems in the manufacturing industry. In our scenario, we should collaboratively assemble a wooden box, emphasizing human-cobot synergy and task partitioning. The main actors of this task are a human worker who is engaged in manual assembly tasks and possess cognitive flexibility and emotional responsiveness, and a cobot able to perform precision tasks. Finally, the method selected for sensing the human worker's internal state is by employing an EEG headset. Particularly the headset was an Emotiv Epoch Plus. Secondly, we created a profile for the human worker. To generate this profile, the human worker had to perform several tests to acquire enough data of his responses while performing the assembly task. By analyzing the acquired data, it was concluded that the most relevant states for this task were stress, engagement, and focus, having a greater weight the stress. Additionally, with the data, it was possible to define the human worker's state baseline and ranges for the task. This allowed us to define 4 levels of intensity for each state: high, mid-high, mid-low, and low. Thirdly, we should develop the robot's adaptation to the detected emotional and cognitive states. To achieve that, we started by programming the movements that the cobot needed to perform in each step and task to fulfill the whole assembly. Mainly the role of the cobot in this task was to grab and hold in a comfortable position for the human worker the pieces of the box to be assembled. While the robot holds the pieces, the humans screw the bolts to fix the different parts. The movements and actions of the cobot should be precise and task-oriented to align with the assembly requirements. Then, we defined which cobot's parameters should be updated to perform the adaptation. In this case, we assessed that by updating the velocity at which the cobot executes its movements and the time lapse between assembly steps performed by the cobot, we could influence positively the internal state of the human worker. Next, we developed the decision-making algorithms that interpret EEG headset data in real time. The algorithms were based on the data acquired in the testing process and the profile of the human worker. Finally, we established a loop between the result of the algorithms using the EEG headset data and the cobot's control system. This loop enabled the cobot to perform dynamic adjustments and responsive behaviors. In this slide, you can take a closer look at the use case diagram of the described application. The main actors performing the use cases are the user wearing the headset, the cobot, and the application. Now in this slide, you can take a closer look at the sequence diagram of the emotion-driven human-cobot interaction application. We can see how the process starts with a request to the server of the EEG headset to get the sensed data. Once the application gets the data, it classifies as high, mid-high, mid-low, or low, considering the user's profile. The last step is to send the information to the cobot server for it to update its speed and delay parameters according to the results of the previous classification. Before finalizing the block of emotional cognitive adaptation, we are going to see 4 more examples of how this type of adaptation can be applied. The first one is a robot that we have seen in the first sci-fi example of a Star Wars series, but this time is real. Walt Disney Imagineering has developed the BD-1 robot, which communicates emotion with its body language and sound. The way of expressing emotion with movements and sounds facilitates its communication and acceptance with humans.
Look over there. Look.
When talking about emotional cognitive adaptation, we have focused on examples where the robots performing the adaptation did not have a face. But what happens if the robot has a face? In this case, the robot could also perform adaptations in their facial expression. Taking this into consideration, I want to introduce you to the concept of uncanny valley. The uncanny valley refers to the unsettling feeling or negative reaction that people may experience when encountering robots or animated characters that appear almost but not exactly human-like. We have 2 axes on the graph. On the abscissa, we have human likeness, and on ordinate, the affinity. As we increase the value of human likeness, the value of affinity towards the robot also increases until we arrive at a certain point of human likeness where the affinity drops to negative. After that, increases its value again after an increase in human likeness. This range of human likeness where the affinity decreases until it recovers to a certain positive value is what we call the uncanny valley. In the slide, there are some examples of robots considered uncanny by some humans. The uncanny valley concept is important for the next examples we are going to see. The following examples show robots developed by Engineered Arts. We are going to see how Engineered Arts has progressed in its development towards communicating emotions with facial expressions on robots. The first example is the Mesmer head Adran. In this second example of Engineered Arts, we can see some of the mechanisms that create the expressions behind the skin of the robots. Lastly, the last example from Engineered Arts is their robot Amica. We can see how there is a great improvement in the facial expressions of the robot. To culminate with this seminar, we are going to share some conclusion points about intuitive human-robot interactions. Firstly, the nature of human-robot interactions is heavily influenced by its purpose, environment, or target users, making contextual information a key aspect of a good interaction. Secondly, achieving intuitive human-robot interactions depends on the use of one or multiple methodologies, including robot commanding, teleoperation, XR interactions, and emotional cognitive adaptations. Thirdly, to be able to develop and apply methodologies of intuitive human-robot interactions, it is necessary to use wearable devices such as data gloves, XR headsets, EEG headsets, eye-tracking glasses, EMG bands or RMM bands. Fourthly, ensuring minimal latency between devices and robots is crucial to achieving real-time, responsive interactions. Fifthly, mitigating noise in signals emerges as critical as it safeguards data accuracy and increases the reliability of the interaction. Sixthly, performing emotional cognitive adaptations necessitates comprehensive user data, personalized and context-aware. This ensures a proper adaptation to the internal states of a person in a particular scenario. Lastly, the majority of the processes for developing intuitive human-robot interactions are data-driven, which is key for having functional algorithms for each type of interaction. Here we finalize this presentation. These are the two responsible authors of this presentation of the seminar. In case any doubts arise, do not hesitate to contact them. In case you want to know more about the exposed topics, this is the literature that has been used for this presentation. I hope you have enjoyed this presentation of intuitive human-robot interactions. Thank you for attending and see you in the next one.